We are studying what happens with the current and the voltage in a purely resistive circuit. We are trying to understand how they are related. So why is that their relation will be different than what we have seen till now? That we'll understand in subsequent videos. But for now, we'll just take up something called as purely resistive circuit, wherein we have AC source. So we have an AC source, we have a resistor. Of course, we can connect a capacitor then, but it won't be a purely resistive circuit. A circuit is purely resistive when we have resistors only. Not a single resistor, it can be any number of resistors, but resistors basically. So when we switch it on, right, the instantaneous voltage is given by this, or you can read it, not write it. Actually, sorry, you can write it as E naught sine omega t, either ways. And your current will be, say, I, which is given by I naught sine omega t, or let me call it as I, and say this resistance is R. So this is said to be purely resistive. A circuit containing only a pure resistance of R ohms is a AC circuit. Is a AC purely resistive circuit actually. This definition is wrong. This is a definition for purely resistive AC circuit. Now let's look at the math. Let's try to relate V and I. I know it should be quite simple. In this case, V is your E of t and I is your I of t. That's a better heading. Again, I can use epsilon or E. So let me go with your textbook representation only. Now let's consider a AC source and just a resistor in that source, connected to that source. So the alternative EMF instantaneous value is given by sine omega t into the maximum value, epsilon naught. Next is current voltage relationship. If I be the current in a circuit at instant t, then the potential drop across R will be. So this we know, this will be nothing but V is equal to I into R. Right, this is a basic relationship. Right, in this case I can just do this. I can't do that, sorry. This is across the resistance R. We're just writing that expression. Right, this is from our old understanding of a simple circuit, Ohm's law. Then according to Kirchhoff's loop rule, so if I take up a circuit, this circuit itself, if I apply the Kirchhoff's law over here, so this is I into R, this is epsilon. So epsilon, or let me write it this way, are instantaneous EMF of the source is equal to instantaneous potential difference across R, right? That's what our Kirchhoff's loop rule helps us to find out. Now, instantaneous EMF is given by epsilon naught sine omega t, and the voltage drop is IR across the resistance. Agree, guys? Now, if I rearrange or divide with R both the sides, so I will be equal to epsilon naught by R sine omega t, and this is your maximum current, omega t. Agree? So why is that we did it? We have already done this before. So why is that exclusively we did that over here? The reason being this. When I compare our instantaneous voltage and current, let's look at their expressions. I naught, I naught. All till now it's same. Sine omega t and sine omega t. When this is same. So what can we tell? That they are in phase. They are in sync. This quantity are constant. That will not change. What will change is this. These are your varying values. But we can see that they are the same, right? In this case, they are the same expression. So when they have the same expression, what can we tell? That they are in phase. And that's what we are trying to prove. In the next set of videos, we'll see that things can be out of phase. Okay. So in this particular situation, the graph, if this is your voltage graph, your current graph might look like this. Of course, the amplitude can vary, but the point wherein they cross the maximum and minima, that will be fixed. Time at which the maximum is passed, right? At the same time, the maximum of the current also will be seen. So basically, your Phasor diagram will look like this. So that's your maximum voltage. That's your maximum current. They'll be in phase. And that's that. In the next set of videos, we'll understand things can be out of phase. And then you will appreciate this particular video.